Okay, section 7.4, estimating the population proportion with confidence intervals. So imagine a large population of people, such as 100 million registered voters in the U.S. Let's again assume that 50% of them will vote for the Democratic candidate in the next presidential election. Suppose ABC News takes a simple random sample of 100 registered voters and asks them which candidate they are going to vote for in the next presidential election. So can we use the central limit theorem to create the sampling distribution for p hat, which is the proportion of people that will vote for the Democratic candidate in a random sample of 100 registered voters? So we need to check those three conditions for the central limit theorem. So remember that condition 1, get the marker turned on. This condition talks about the center, so it's interested in bias. So is the sample collected randomly from the population, and are the observations independent of each other? We can say yes, it was a random sample, and that one person's preference for candidate's not going to have an effect on another's. Right? And the sample can be collected with or without replacement. Right? Condition 2 has to do with shape, and it's interested in sample size. So we're checking to see whether the sample size n is large enough that the sample expects at least 10 successes and 10 failures. Right? So our sample size is 100, p is 0.5, so that gives us 50. And here our sample size is 100, and 1 minus 0.5 gives us 50 as well. So here we can say yes, our sample size is big enough. And just to be consistent, I'm going to go back to condition 1 and put a yes there. All right, condition 3, remember, was important because it affected spread. So condition 3, if the sample is collected without replacement, okay, which I think we were told these were simple random samples. Let's see. Simple random sample, so it was without replacement, then we need to make sure the population size is at least 10 times bigger than the sample size. So we've got 100 million registered voters. That's our capital N, our population size. Is that bigger than or equal to 10 times our sample size of 100? And we can say yes, that's definitely bigger. All right, so then moving on, since these conditions have all been met, we can use the central limit theorem to create the sampling distribution for p hat. So let's draw the normal model for the sampling distribution below. So keep in mind the sampling distribution is going to be normal, should be centered at 0.5, should have a standard error equal to 0.5 times 1 minus 0.5 over the sample size of 100, which means it's going to be approximately normal, center at 0.5, and a standard error of 0.05. So now we can draw that. So there's our shape. Here's our center. If I use our standard errors, 1, 2, and 3, and 1, 2, and 3, we're going to have 0.55, 0.6, and 0.65. And counting back, 0.45, 0.4, and 0.35. And let's see if I can squish this in. Down here, these are sample proportions. So the proportion of a sample that indicates they're going to vote for the Democratic candidate. All right, so according to the sampling distribution, what percentage of the sample should we expect to express support for the Democratic candidate? We should expect 50%. That's our middle value, our mean. So give or take a little bit. I mean, within 1 standard deviation would be a good expectation. So we could also say around 0.5, give or take 0.05. And if we want to be even more confident, we widen that interval a little bit. And then the last question here, what's the probability that the sample proportion will fall within 2 standard errors of the population proportion p? So within 2 standard errors, so from here to here, remember your empirical rule, that should be about 95%. So based on the empirical rule, which applied to normal distributions, that should be around 95% of your samples. Okay, so number 2, our conclusion that we should expect our sample proportion to be 50%, give or take 5 percentage points, is useful because it implies that in general we can predict where p hat will fall relative to p. It indicates that p hat is very likely to fall within 2 standard errors of the true value of p, as long as the sample size is large enough. If we have a small standard error, then we know that p hat is quite likely to fall close to p. And close if you have a small standard error. right, so here's a really big idea. If we can predict that p hat will fall close to p, and we see that in our sampling distributions, then we can turn the tables and we can predict that p will be close to our sample proportion p hat. Right, so this is going to be helpful when you don't know p. All right, so let's return to the more realistic situation of not knowing the value of p. All right, a simple random sample, so we've got SRS of 1,200 Americans aged 20 and over contained 138 diabetics. In this case, we have access to the sample data, but not the entire population. This means we can calculate p hat, but not p. So what is p hat? Well, p hat is the proportion of our sample that is diabetic. So we have 138 out of 1,200, which is 0.115, or 11.5%. All right, so just on a side here, remember that p hat is the proportion of the sample that's diabetic. And p is the proportion of the population that's diabetic. All right, so is this estimate unbiased? We can say yes, because the sampling method was unbiased. And that was indicated by them telling us they used a simple random sample. Okay, so we're going to estimate the standard error. And this is an estimate because we don't know p. Okay, and this is equal to, and it was our p hat was 0.115. And this needs to be in decimal form for this to work. And our sample size is 1,200. Again, you should grab a calculator and verify this. You get a standard error, estimated standard error of 0.0092. All right, so what does this estimated standard error tell us? Well, it gives us an idea of how spread out the p hats are likely to be. In other words, it gives us the typical distance from p. So on average, how far away from p are your p hats? Okay, and then next bullet, what do we know about the sampling distribution for p hat? Well, if we use the central limit theorem to talk about that sampling distribution, we should check those three conditions first. So, is there a random sample? We can say yes. And are your observations independent from each other? And yes, we can say that because one person's diagnosis has no effect on the next person's. Second thing, we should check our sample size. Right, so we want to do those two calculations, check to make sure they're both bigger than 10. So this gives us 1,200 times 0.115, which is 138, and 1,200 times 1 minus 0.115, which is 1,062. So we can say that one's been met too. In fact, we'll go back, we'll check off that third one. All right, in the third condition, we want to check our population size and make sure it's at least 10 times bigger than our sample size. So we're going to check to see if the number of Americans is greater than 10 times 1,200. And I think it's safe to conclude that that is true. So we can check that one off too. So what does our sampling distribution look like? Well, since all the conditions have been met, we know the shape is going to be normal. You know the center is going to be at p. And notice I don't have a value for p, so I can't put a number in there. And I know that it's going to be about 3 standard errors will take me to the end of the distribution, and about 3 standard errors will take me to the end of the distribution on the left. And again, I can't fill in any numbers, so all I can say is this is what it would look like in terms of shape and center and spread. All right, so our sampling distribution of p hat normal, centered at p, which again we don't have the value for, and we maybe can put our standard error that's estimated in here. We get kind of an idea of how spread out it is, but we don't have the exact standard error yet. All right, so what else can we conclude? Well, we can be highly confident that the population parameter p is between these two numbers. Since we know p hat should be within 3 standard errors of p, then again we're reversing the tables and saying p should be within 3 standard errors of the p hat we found. So here's our p hat. Here's 3 standard errors. And if you remember from the previous page, our standard error was points, and this again was an estimated standard error, was 0.0092. And if we triple that, we get about 2.76%. So again, I'll leave that up to you to double check that. And if we simplify that, carry out the subtraction, we get this value. Carry out the addition, we get that value. So this is an example of a confidence interval. This confidence interval could also be reported in the following form. So we could say 11.5% give or take, or plus or minus 2.76%, or we can say it out in words, plus or minus. So confidence intervals report the sample proportion plus or minus some amount. The some amount is called the margin of error, sometimes abbreviated MOE, which tells us how far from the population value our estimate is likely to be. So our confidence intervals provide 2 pieces of information: a range of plausible values for a population parameter p, and a confidence level, which expresses our level of confidence in this interval. And they are calculated as follows. And we take our sample result, or statistic, p hat, and we add and subtract our margin of error. And our margin of error is just a couple of standard errors. All right, so we select a margin of error based on our desired confidence level. The following diagram shows 4 different margins of error for a sample in which p hat is 11.5%, and the estimated standard error is 0.92%. All right, so notice p hat's right here in the middle. If I go 1 standard error to the right and 1 standard error to the left, that's going to give us a confidence level of 68%. If I go 3 standard errors to the right and 3 standard errors to the left, that's going to give us a confidence level of 99.7%, and that's what we had above. So then red, this one was given in number 4. And the one in the middle, you're curious, you want to use 2 standard errors, that's going to give you a confidence level of 95%. Okay, so let's consider what is meant by a range of plausible values for a population parameter p by taking another look at our simple random sample of 1,200 Americans aged 20 and over, in which 138 people were diabetics. Reminder, in this case, we have access to the sample data, and we were able to calculate p hat, which is 11.5%, and that came from taking 138 and dividing by 1,200. But we don't know the population proportion p. So the question is, which of the following sampling distributions for p hat, the proportion of diabetics in a sample of 1,200, could have produced the p hat value of 11.5%? So if that was what we got in our sample, and we come down and look here, if p is 0.095, this gives us standard error. Notice that StatCrunch calls it a standard deviation. It gives us a standard error of 0.0085, and it produces this sampling distribution. So if that's really what p was, notice that our p hat is right here. And so the question is that too far away? For us to conclude that p could have been 0.095. That's the question we're interested in, is that too far away? Well, if we move on to another example, with maybe contrasting it, we'll have a better idea. So let's say that the mean, P, is 0.1. So notice that's the center of this distribution. That gives us a standard error of 0.0087, and it puts our P hat value right here. And now we're closer to the middle, so now this looks like maybe a better candidate for P. And if we keep moving along and check the means of these distributions and where P hat, our P hat happens to be, find that there's a bunch of them where P hat is close enough to the middle that we would assume that it would be an okay distribution for it to have come from, or a likely candidate for P. So I'm going to keep moving down. Here's 11.5%. Here's 11.5%. And then this last one, we might start getting so far away to the left that we again call this into question. Is this too far away from the center for us to conclude that P could be 0.135? So again, if P is 0.135, is our P hat likely to have come from that sampling distribution? Okay. So I would say that all of these are likely candidates. Our P hat's somewhat near the center of each of those, but the two on the end may be too far away. So even just looking at those, let's see, we've got 1, 2, 3, 4, 5, 6, 7 distributions where P hat is a likely candidate to have come from. We still, in this last question here, would say no, these aren't the only sampling distributions that our P hat could have come from. In fact, any P between the ones given above would also work. So P could have been 0.1, let's see, we had 0.105 and 0.1. It could have been 0.102. It could be 0.112 or 0.123. So anything in between the ones we have above would also work. Okay, a confidence interval provides a range of plausible values for a population parameter P. This means that all the values in the interval, and not just the endpoints, are plausible values of P. It also means that our sample result, P hat, is a plausible result given a sampling distribution for any value of P within our confidence interval. All right, so let's return to our first scenario where P was known, so we can get a better sense of what the confidence level means. Following is a normal model for the sampling distribution for P hat, proportion of people that will vote for the Democratic candidate, and a random sample of 100 registered voters when P is 50%. So in this case, our sampling distribution for P hat is approximately normal. And we did check the conditions earlier, so I'm not going to run through those again, but I'll leave it up to you to double check. At a center at 0.5 and a standard error at 0.05. And the standard error came from the formula P times 1 minus P over the sample size of 100. All right, so here's our center, and the shape is normal. And if we go 1, 2, 3 standard errors to the right, and 1, 2, 3 standard errors to the left, and label our horizontal axes. Oops, let me undo that. This should say sample proportions. Okay, so in part A, one student decides to take a random sample of 100 registered voters and finds a P hat of 45%. The student then calculates a confidence interval using 2 standard errors. Will this interval capture P? So keep in mind 45% is the same as 0.45. So if we do 0.45 plus or minus 2 standard errors, and your standard error is 0.05, we get the interval 0.35 up to and including 0.55. So we would say yes, this interval works. So here's that sample result, that particular student's P hat up on our table, our graph above. 2 standard errors above would bring us to the right-hand side of their interval. 2 standard errors to the left or below is the left side of this interval. And notice it includes P. So that's why we say that that interval captures P or is a successful interval. And on the other hand, another student decides to take a random sample of 100 registered voters, finds a P hat of 38%. This student calculates a confidence interval using 2 standard errors. Will this interval capture P? So 38% plus or minus 2 standard errors. So we've got 0.38 plus or minus 0.1 gives us the interval of 0.28 up to 0.48. And so if we look up here, let's mark where their p-hat is. Notice their p-hat's a possible value. It's on that interval. It's in that distribution. But when we create our interval up to 0.48 and down to, what was our lower end, 0.28, it's off the chart, that interval's not successful. It doesn't capture p, because p, remembers, right here. It's outside that interval. And so then the question becomes, what proportion of the p-hats in our sampling distribution will produce a successful confidence interval using 2 standard errors, and what proportion won't work? So let's put the ones that work on the right, on the left, and the ones that don't work on the right. So if you're going to go 2 standard errors above and below, that means any of these p-hats in this interval that I'm shading in blue are going to work. And that's 95% of your sample results. And the ones that don't work are the ones that are too far away or that are in these tails. And so these 2 tails combined have an area of 5%. So 5% of the sample portions are so far away that they're not going to work. And again, it doesn't mean that you did anything wrong. It just means that you're maybe a little bit unlucky. You got a sample result that's so extreme that this process of creating a confidence interval doesn't give you an interval big enough or wide enough to capture p. Okay, so the confidence level tells you how often the estimation method is successful. Our method is to take a random sample, calculate p-hat, and then calculate a confidence interval to estimate the population proportion. So if the method has a 100% confidence level, then the method always works. If the method has a 95% confidence level, then the method works 95% of the time, or for 95% of the sample proportions. If the method has a 10% confidence level, then the method works in 10% of the intervals. And keep in mind up here, if we want an interval to always work, we're going to need to have our interval start at 0% and go all the way up to 100%. So although it's appealing to think about an interval that would always work, 100% confidence, this interval doesn't really tell us much about where p is. All right, so back to here. We say that the method works if the interval captures the true value of the population parameter. In other words, the interval works if the true population proportion is inside the interval. Keep in mind that the population proportion doesn't move. It is always the same. And your population proportion is p. However, the confidence interval does change with every random sample collected. Thus, the confidence level measures the success rate of the method, not of any one particular interval. All right, so how do you choose a level of confidence? Let's take another look at the diagram illustrating the 4 different confidence levels. And this isn't the only 4 possible. You can certainly do other ones as well. All right, so notice that if we increase the margin of error from 2 standard errors, so here's 2 standard errors, and that has a confidence level of 95%, up to 3 standard errors, which has a confidence level of 99.7%, you're only gaining a small amount of confidence, and you're going from 95% confidence to 99.7% confidence. If you decrease the margin of error from 2 standard errors down to 1, so here's 1 standard error, that has a 68% confidence level, you lose a lot of confidence. Confidence level falls from 95% to 68%. So the most common margin of error, confidence level is 95%. So though the most common level of confidence is 95%, others can also be used. The following table summarizes the margin of error for 4 commonly used confidence levels. In commonly used, it doesn't mean it's an exhaustive list. So you need 99%, 95%, 90%, 80%. Notice these 3 are not in the table above or in the picture above, so we've got even more examples. Also notice for 95% confidence level, we're not actually using 2 standard errors, but we're using the more exact value of 1.96 standard errors. Okay, so the formula for confidence interval is p-hat plus or minus m, so that's your sample statistic, or sample proportion more specifically, plus or minus your margin of error, or MOE for short. Your margin of error more specifically is going to be a couple of estimated standard errors. So Z star tells you how many standard errors. And your standard error, your estimated standard error, is calculated with this formula, same one we've been using. All right, so a few notes. M, again, is your margin of error, or MOE for short. P hat is the sample proportion of successes, or the proportion of people in the sample with the characteristic we're interested in. N is your sample size. Z star, so in this symbol Z with the asterisk next to it, is read as Z star. Okay, it's a multiplier that is chosen to achieve the desired confidence level, and is sometimes referred to as a critical value. And SE with EST as a subscript is your estimated standard error. So estimated, again, because you don't have P, or you don't know the value of P. So a reminder, this formula depends on the central limit theorem conditions being met. All right, so 15, how do you interpret a confidence interval? Let's use a confidence interval we've already calculated. So we found that the 99.7% confidence interval for the proportion of diabetics in the population was 8.74% to 14.26%. And this, remember, was 3 plus or minus 3 standard errors, plus or minus 3 estimated standard errors. All right, so the confidence interval tells us that any value between 8.74% and 14.26%, and that's inclusive, so it also includes those two numbers, any of those is a plausible value for the percentage of diabetics in the population. And the percentage of diabetics in the population is represented by P. All right, and secondly, any value outside this confidence interval is not a plausible value for the percentage of diabetics in the population. It's not impossible that the population value is outside this confidence interval, but it would be very surprising if it were. All right, and then we can interpret this confidence interval as follows. We can be 99.7% confident that the percentage of people with diabetes in the population is between 8.74% and 14.26%. And we can also say if we were to repeat this survey many times, then in 99.7% of the surveys, the resulting confidence interval would succeed in capturing the percentage of diabetics in the population. All right, and last note here at the bottom, our confidence is in the process that produces the confidence interval, not in any one particular interval. So it's incorrect to say that a particular confidence interval has a 95% or any other percent chance of including the true population parameter. Remember, the population parameter's value is fixed. It's not moving. So instead, we say that the process that produces confidence intervals captures the true population parameter with a 95% probability.